Hello there, and welcome. Tonight I want to take you somewhere extraordinary, somewhere that exists at the intersection of scientific discovery and cosmic mystery. Settle in, make yourself comfortable, and allow your mind to drift as we embark on a journey through one of the most intriguing puzzles our universe has recently presented to us. Before we begin this peaceful exploration together, I'd like to know where you're joining us from tonight. Take a moment, if you feel inclined, to share in the comments below what time it is where you are, and from which corner of our beautiful planet you're listening. There's something profoundly connecting about knowing that people all around the world, at different times of day and night, are contemplating these same cosmic mysteries together. And if you find yourself drawn into this gentle journey through space and wonder, perhaps you might consider subscribing to join us for more explorations of the universe's quiet mysteries, and leaving a like to help others discover these peaceful voyages through the cosmos. It's October 19th, 2017, and high atop a dormant volcano in Hawaii, the Pan-STARRS telescope is conducting its nightly vigil, scanning the darkness for asteroids that might pose a threat to Earth. The telescope, whose name stands for Panoramic Survey Telescope and Rapid Response System, has been doing this patient work for years, cataloguing the movements of countless rocks tumbling through our solar system. But on this particular night, something different appears in the data stream. A faint point of light, moving rapidly against the background stars, catches the attention of astronomer Robert Verick as he reviews the observations. At first, it seems like just another asteroid, perhaps one on an unusual trajectory. But as he begins to calculate its path, something extraordinary emerges from the numbers. The object is moving too fast, far too fast to be bound by our sun's gravity. Its trajectory is hyperbolic, a mathematical curve that tells a story of incredible speed and cosmic distance. This isn't just another piece of our solar system's debris. This is something that has come from somewhere else entirely, from the vast emptiness between the stars. For the first time in human history, we have detected an interstellar visitor, an object that formed around another star, perhaps millions or even billions of years ago, and has been travelling through the cosmic darkness ever since. The realization sends ripples through the astronomical community, a quiet excitement that spreads from observatory to observatory as telescopes around the world turn to track this unprecedented visitor. They name it ʻOumuamua, a beautiful Hawaiian word meaning scout or messenger from afar arriving first. The name is chosen by the Pan-STARRS team, honouring both the Hawaiian origins of the discovery and the profound nature of what has been found. There's something poetic about this name, something that captures both the scientific significance and the deeper wonder of this moment. A messenger from afar arriving first, it suggests that this might be just the beginning, that ʻOumuamua might be the first of many such visitors we'll detect as our technology improves and our eyes on the sky become ever more vigilant. As astronomers gather more data over the following days and weeks, ʻOumuamua reveals itself to be even stranger than initially thought. Its brightness varies dramatically as it tumbles through space, suggesting an elongated shape unlike anything we've seen in our own solar system. Imagine, if you will, a cosmic needle, or perhaps a flattened disk, spinning end over end every 7 1/3 hours as it hurtles through the darkness. The brightness variations are extreme, suggesting that this object might be 10 times longer than it is wide, a ratio that defies our understanding of how natural celestial bodies typically form. Consider for a moment the journey this object has taken to reach us. ʻOumuamua entered our solar system from above the plane where all the planets orbit, diving down at an angle that brought it close to the Sun before swinging back up and away. Its approach velocity was about 26 kilometers per second relative to our Sun, a speed that speaks of vast distances crossed and timescales that dwarf human comprehension. To put this in perspective, if you could travel at ʻOumuamua's speed, you could circle the Earth's equator in about 25 minutes. You could reach the Moon in 4 hours. And yet, even at this tremendous velocity, ʻOumuamua has likely been travelling for millions of years to reach us from its point of origin. The trajectory analysis reveals that ʻOumuamua came from the direction of the constellation Lyra, though not from any particular star we can identify. This is because over the vast time scales of interstellar travel, stars themselves move and shift position. The star that gave birth to ʻOumuamua might be nowhere near where it was when this object began its journey. We're looking at a messenger from not just another place, but another time, a fragment of cosmic history that has been preserved in the cold vacuum of space, while entire civilizations might have risen and fallen on countless worlds. What makes ʻOumuamua particularly intriguing is how different it is from what we expected an interstellar visitor to be. For decades, astronomers had predicted that the first interstellar object we detected would likely be a comet, a dirty snowball of ice and rock that would announce its arrival with a spectacular tail as it approached our Sun. Comets, after all, are more easily ejected from star systems during the chaotic early stages of planetary formation, and their bright tails make them easier to spot from great distances. But ʻOumuamua showed no signs of cometary activity. No tail, no coma of gas and dust surrounding it, no visible outgassing despite passing relatively close to our Sun. It appeared to be a dark reddish object, its surface perhaps covered in complex organic molecules that have been irradiated over eons of cosmic travel. The colour itself tells a story. That reddish hue is similar to what we see on some objects in the outer reaches of our own solar system. Surfaces that have been exposed to cosmic rays for billions of years. These high-energy particles streaming through space from distant stellar explosions and other cosmic events gradually alter the chemistry of exposed surfaces, creating complex carbon-rich compounds called tholins. If ʻOumuamua's surface is indeed covered in such materials, it suggests an incredibly long journey through interstellar space, a voyage measured not in years or centuries, but in geological epochs. As we contemplate ʻOumuamua tonight, it's worth reflecting on the profound shift in perspective it represents. For all of human history until that October day in 2017, every object we'd ever observed in our solar system, every planet, moon, asteroid and comet, had formed from the same primordial disk of gas and dust that gave birth to our Sun. They were all siblings in a sense, sharing a common origin story that began about 4.6 billion years ago. But ʻOumuamua is different. It's a stranger, a piece of another star system entirely, formed under conditions we can only imagine, perhaps around a star very different from our own. This realization connects us to the broader galaxy in a tangible way. The Milky Way, our home galaxy, contains hundreds of billions of stars, many of them surrounded by their own systems of planets and smaller bodies. The spaces between these stars, which we once thought of as empty voids, are apparently traversed by objects like ʻOumuamua, silent messengers carrying information about distant stellar systems. How many such objects might there be? current estimates, based on the detection of Oumuamua and the volume of space our telescopes monitor, suggest that there might be trillions of interstellar objects passing through our solar system at any given time. Most are too small or too distant for us to detect, ghost-like presences that slip through our cosmic neighbourhood unseen. The discovery of Oumuamua also raises profound questions about the nature of planetary systems and how material gets exchanged between them. In the early days of a stellar system's formation, when planets are still coalescing from the primordial disk, gravitational interactions can fling smaller bodies out into interstellar space. These ejected objects then wander the galaxy, occasionally passing through other stellar systems like cosmic seeds blown on an interstellar wind. Could such objects carry more than just rock and ice? Could they perhaps carry the building blocks of life itself from one star system to another? This idea, known as panspermia, has been discussed by scientists for over a century, but Oumuamua gives it new relevance. If objects can indeed travel between star systems, and if they can survive the journey intact, then it's possible that life, or at least the complex organic molecules that lead to life, could be distributed throughout the galaxy by these interstellar wanderers. Oumuamua itself, with its reddish, possibly organic-rich surface, might be carrying such molecules, though we'll never know for certain as it is now too far away for detailed study. As we settle deeper into our exploration tonight, consider the timing of Oumuamua's discovery. Humanity has only had the technology to detect such objects for a few decades, and only in the last few years have our survey telescopes become sensitive enough to routinely spot objects of Oumuamua's size and speed. The fact that we detected an interstellar visitor so soon after gaining this capability suggests that such objects might be far more common than we previously thought. We're like people who have just invented the microscope, suddenly realizing that the drops of water we thought were simple and uniform are actually teeming with previously invisible life. The shape of Oumuamua continues to puzzle scientists. That extreme elongation, if confirmed, is unlike anything we see among the asteroids and comets of our own solar system. The most elongated asteroids we know of have length-to-width ratios of about 3:1, but Oumuamua might be 10:1 or even more extreme. How does nature create such an object? One possibility is that Oumuamua is a fragment of a larger body that was torn apart by tidal forces, perhaps during a close encounter with its parent star or a giant planet. The gravitational forces in such an encounter could stretch and fracture a larger object, creating elongated shards that are then ejected into interstellar space. Another possibility, one that captures the imagination, is that Oumuamua's shape is not natural at all. Some scientists, including Harvard astronomer Avi Loeb, have suggested that the object's properties might be consistent with an artificial origin. Not necessarily an alien spacecraft, but perhaps a piece of technology, like a light sail or a defunct probe, created by another civilization and now drifting through space like a message in a bottle, cast into a cosmic ocean. It's a thought that seems like science fiction, and yet it's being seriously discussed in peer-reviewed scientific journals, a testament to how truly unusual Oumuamua's properties are. The idea isn't as far-fetched as it might initially seem. Humanity itself is already developing light sail technology, thin reflective sheets that can be pushed by the pressure of sunlight or laser beams to achieve high velocities. The Breakthrough Starshot project, for instance, aims to send tiny light sail-propelled probes to the nearest star system, Proxima Centauri, within this century. If we're on the verge of creating such technology, why couldn't another civilization, perhaps 1,000 or millions of years more advanced than us, have already done so? And if they have, wouldn't the galaxy be littered with the remnants of their efforts, defunct sails and probes drifting between the stars? As you lie there tonight, perhaps feeling yourself beginning to relax, to drift like ʻOumuamua itself through the peaceful darkness, consider what it means that we live in a universe where such questions can be seriously asked. We're not talking about fantasy or speculation without foundation, but about real observations of a real object that visited our solar system. The data is there, recorded by multiple telescopes, analysed by hundreds of scientists, published in respected journals. ʻOumuamua is real, its properties are genuinely puzzling, and the questions it raises go to the heart of our place in the cosmos. The reddish colour of Oumuamua's surface speaks to the vast timescales involved in interstellar travel. Cosmic rays, those high-energy particles that stream through space, gradually alter any exposed surface, creating complex organic molecules through a process called space weathering. This process takes time, enormous amounts of time. The darker and redder the surface, the longer it has likely been exposed to this cosmic bombardment. Oumuamua's surface suggests millions, perhaps tens of millions of years of travel through interstellar space, a journey that began when our ancestors were still learning to use stone tools, or perhaps even earlier when dinosaurs still roamed the Earth. During this vast journey, Oumuamua has been essentially alone, travelling through the almost perfect vacuum between stars. The interstellar medium, as this space is called, contains on average about 1 atom per cubic centimetre. For comparison, the air you're breathing right now contains about 10 to the 19th atoms per cubic centimetre. Oumuamua has been travelling through a void so empty that it's difficult for our minds, evolved on a planet rich with matter and life, to truly comprehend. And yet it has survived this journey intact, its elongated form tumbling steadily through the darkness, maintaining its rotation for perhaps millions of years. The detection of Oumuamua has sparked a revolution in how we monitor our cosmic neighbourhood. New telescopes and survey programs are being developed specifically to detect interstellar visitors. The Vera Rubin Observatory, currently under construction in Chile, will be able to detect objects much fainter than Oumuamua, potentially discovering hundreds of interstellar visitors over its operational lifetime. Each of these discoveries will add another piece to the puzzle, helping us understand how common such objects are, what they're made of, and where they come from. But Oumuamua will always be special as our first confirmed interstellar visitor. Like the first exoplanet discovered orbiting another star, or the first detection of gravitational waves, it marks a threshold moment in human understanding. We've gone from knowing intellectually that objects must sometimes travel between stars to actually observing one doing so. It's a reminder that the universe is far more dynamic and interconnected than we might imagine from our seemingly stable vantage point on Earth. As we prepare to delve deeper into the specific mysteries of Oumuamua's behaviour and what it might mean, take a moment to appreciate the cosmic perspective this object provides. Every star you see in the night sky is a sun, many with their own systems of planets and smaller bodies. The spaces between these stars, which look empty to our eyes, are actually crisscrossed by invisible highways of objects like Oumuamua, each carrying information about its home system. We live not in isolation, but in a galaxy where matter and perhaps information flow between stellar systems like messages passed between distant islands. The name ʻOumuamua, that beautiful Hawaiian word meaning messenger from afar, seems more appropriate the more we learn about this object. Whether it's a natural piece of another stellar system or something more exotic, it has brought us a message. That message might simply be that we are not alone in the sense that other stellar systems exist and occasionally share their material with us. Or the message might be more profound, hinting at possibilities we're only beginning to imagine. Either way, ʻOumuamua has changed how we see our place in the cosmos, reminding us that our solar system is not a closed box, but an open stage where actors from across the galaxy occasionally make guest appearances. Tonight, as you drift towards sleep, you're participating in a moment of cosmic awareness that would have been impossible for most of human history. You know that our solar system has been visited by an object from another star. You know that right now, as you lie there, ʻOumuamua continues its journey, having passed beyond the orbit of Neptune and heading back into interstellar space. It will never return. Its trajectory ensures that this was a one-time visit, a brief encounter between our solar system and this mysterious messenger. But the questions it raised, the wonder it inspired, and the new way of seeing our cosmic neighbourhood that it provided, these will remain with us. The Pan-STARRS telescope that first spotted ʻOumuamua sits atop Haleakala, a massive shield volcano on the Hawaiian island of Maui. At an elevation of over 10,000 feet, above much of Earth's atmosphere, it's one of the premier sites on our planet for astronomical observation. The name Haleakala means House of the Sun in Hawaiian, and there's something poetically appropriate about this House of the Sun being the place where we first spotted our interstellar visitor. Every clear night, the telescope's 1.8-metre mirror collects ancient light from across the cosmos, light that has been travelling for years, centuries, or even billions of years to reach us. But on that October night in 2017, it captured something different. Light that had been reflecting off an object that didn't belong to our solar system at all. Robert Verick, the astronomer who first noticed ʻOumuamua in the data, wasn't looking for interstellar visitors. He was part of a team whose primary mission is protecting Earth from potentially hazardous asteroids. Every night, Pan-STARRS takes thousands of images of the sky, comparing them to look for objects that move against the background stars. Most of these moving objects are asteroids, chunks of rock and metal left over from our solar system's formation, orbiting the Sun in relatively predictable paths. The software flags anything that moves, and human astronomers review the most interesting candidates. It's patient, methodical work, like panning for gold in a stream of data, looking for nuggets of scientific importance among the countless grains of ordinary observations. When Verick first saw the data points that would turn out to be ʻOumuamua, something about the object's motion caught his attention. It was moving fast, unusually fast, and its trajectory didn't match any known asteroid. He checked earlier observations, finding that the object had actually been captured in images from the previous night, but had been missed by the automated detection software because it was moving so rapidly. This retroactive discovery is common in astronomy. Often, once we know where to look, we find that an object has been hiding in plain sight in archived data, waiting for someone to notice its significance. The initial observation suggested something extraordinary, but extraordinary claims require extraordinary evidence. Verick and his colleagues immediately began the process of calculating the object's orbit with greater precision. This involves taking multiple observations of the object's position over time, and using the laws of celestial mechanics to determine its path through space. For objects within our solar system, these calculations typically yield elliptical orbits around the Sun. But as more data points were added for this new object, a different picture emerged. The orbit wasn't elliptical, it was hyperbolic, a trajectory that could only mean one thing. This object was not gravitationally bound to our Sun and must have come from interstellar space. The realization triggered a flurry of activity in the global astronomical community. Within hours of the discovery being announced, telescopes around the world were turning toward ʻOumuamua, the European Southern Observatory's Very Large Telescope in Chile, the Gemini North Telescope in Hawaii, the Hubble Space Telescope orbiting above Earth's atmosphere. All focused their powerful eyes on this small, fast-moving object. Time was of the essence because ʻOumuamua was already heading away from Earth, growing fainter with each passing day. The astronomical community had perhaps a few weeks at most to gather as much data as possible before the object became too faint for even our most powerful telescopes to detect. What emerged from these observations was a portrait of an object unlike anything in our solar system. The brightness of ʻOumuamua varied dramatically as it rotated, far more than typical asteroids. Imagine a pencil spinning end over end. When you see it from the side, it appears long, but when you see it end on, it appears as just a small circle. ʻOumuamua's brightness changed by a factor of 10 as it rotated, suggesting an extremely elongated shape. This rotation period of about 7.3 hours was determined with remarkable precision by combining observations from multiple telescopes around the world. A beautiful example of international scientific collaboration in action. The colour of ʻOumuamua provided another piece of the puzzle. Spectroscopic observations, which analysed the specific wavelengths of light reflected by the object, revealed a reddish hue similar to some objects in the outer solar system. This colour is thought to result from cosmic radiation processing organic molecules on the surface over vast periods of time. It's as if ʻOumuamua wears its age on its surface, the reddish patina a testament to eons of travel through the harsh environment of interstellar space. Yet despite this coloration suggesting the presence of organic molecules, ʻOumuamua showed no signs of the volatiles, water ice, carbon dioxide, methane, that we would expect to see in a comet. The absence of cometary activity was perhaps the biggest surprise. Comets in our solar system are essentially dirty snowballs, mixtures of ice and rock that develop spectacular tails when they approach the Sun. The Sun's heat causes the ice to sublimate directly into gas, creating a cloud of material around the comet's nucleus, and often a long tail pointing away from the Sun. Given that ʻOumuamua passed within 0.25 astronomical units of the Sun, closer than Mercury's orbit, astronomers expected to see at least some outgassing if it contained any volatile materials. But repeated observations with the most sensitive instruments available detected nothing. No coma, no tail, no spectroscopic signatures of common cometary gases. This absence of outgassing was so unexpected that some astronomers initially wondered if their instruments were malfunctioning. Multiple independent observations were conducted to confirm the null result. The Spitzer Space Telescope, with its ability to detect infrared radiation that would be emitted by warm dust particles, found nothing. Ground-based telescopes equipped with specialized filters designed to detect specific gases found nothing. ʻOumuamua appeared to be completely inert, a dry rock tumbling through space, despite having just made a close pass by our Sun that should have activated any volatile materials present. The size of ʻOumuamua could only be estimated indirectly, as the object was too small and distant to resolve as anything more than a point of light in our telescopes. Based on its brightness and assuming a certain reflectivity, astronomers estimated it to be somewhere between 100 and 1,000 meters in its longest dimension. If it's on the smaller end of this range and highly reflective, it might be about 100 meters long and perhaps 10 meters wide. Imagine a football field-sized needle tumbling through space. If it's darker, and therefore larger to produce the same brightness, it could be up to a kilometre long, though still maintaining that extreme aspect ratio that makes it so unusual. The tumbling motion itself tells a story. Objects in space tend to rotate around their axis of greatest inertia. Essentially, they settle into the most stable rotation possible. The fact that ʻOumuamua is tumbling rather than spinning smoothly suggests it may have been disturbed relatively recently in astronomical terms. Perhaps it had a close encounter with a planet or star that set it tumbling, or perhaps it experienced a collision that knocked it into this complex rotation. The tumbling motion made observations more challenging but also more informative, as it allowed astronomers to see the object from multiple angles as it rotated. As days turned into weeks, the observational campaign intensified. Radio telescopes were brought into play. Listening for any artificial signals that might indicate ʻOumuamua was more than just a natural object. The Green Bank Telescope in West Virginia, one of the world's most sensitive radio telescopes, spent hours listening to ʻOumuamua across a wide range of frequencies. The SETI Institute's Allen Telescope Array also joined the search. While no artificial signals were detected, the very fact that such observations were seriously undertaken shows how unusual and intriguing ʻOumuamua's properties were. This wasn't wild speculation, but careful scientific investigation of an object that defied easy categorization. The trajectory of ʻOumuamua through our solar system was carefully reconstructed from the observations. It entered from above the ecliptic plane, the imaginary disk in which most planets orbit, at an angle of about 123 degrees. It passed closest to the Sun on September 9th, 2017, about 6 weeks before its discovery, swinging around our star in a hairpin turn that changed its direction of travel by about 66 degrees. At its closest approach to Earth on October 14th, it was about 24 million kilometers away, or about 60 times the distance to the Moon. By the time it was discovered 5 days later, it was already heading away, racing toward the constellation Pegasus. The velocity of ʻOumuamua relative to the Sun was another remarkable aspect of its visit. Before entering our solar system, it was travelling at about 26 kilometers per second relative to our star. This might seem incredibly fast, and it is by earthly standards, but it's actually quite slow for an interstellar object. In fact, it's close to the average velocity of stars in our local neighbourhood of the galaxy, something called the local standard of rest. This led some astronomers to suggest that ʻOumuamua might not have been ejected from its home system at high velocity, but instead might have been gently drifting through interstellar space, almost at rest relative to the average motion of nearby stars. This relatively slow approach velocity has profound implications. If ʻOumuamua was violently ejected from its home system, we would expect it to have a much higher velocity relative to the local stars. The fact that it was moving slowly suggests either a gentle ejection mechanism or that it has been travelling for so long that gravitational interactions with passing stars have averaged out its motion. It's as if ʻOumuamua was floating in the galactic stream, moving with the current rather than swimming against it, until our solar system happened to pass by and briefly captured it in our gravitational influence. The discovery process itself reveals something beautiful about modern astronomy. Within days of Verrick's initial detection, astronomers around the world were coordinating observations, sharing data, and collaborating on analyses. Telescopes that cost hundreds of millions of dollars were rapidly reprogrammed to observe this visitor. Scientists who might normally be competitors for telescope time and research grants worked together with remarkable cooperation. The Minor Planet Electronic Circulars, the official channel for announcing asteroid discoveries, buzzed with updates about Oumuamua's position and properties. Scientific papers were written, submitted and published at unprecedented speed. The entire global astronomical community came together to study this unique object before it faded from view. The naming of Oumuamua also reflects this spirit of international collaboration and cultural respect. The International Astronomical Union, which has the responsibility for naming celestial objects, accepted the Hawaiian name proposed by the Discovery team. The full official designation is 1I/2017 U1 Oumuamua, where the 1I indicates this is the first interstellar object ever catalogued. But it's the name Oumuamua that has captured public imagination. The choice to use a Hawaiian name honours the indigenous culture of the place where the discovery was made, and acknowledges that modern astronomy often operates on lands that have deep cultural and spiritual significance to indigenous peoples. As Oumuamua continued to recede from the sun, something unexpected happened that would add another layer to its mystery. Careful analysis of its trajectory showed that it wasn't following the path predicted by gravity alone. There was an additional acceleration, small but measurable, pushing Oumuamua away from the sun. This non-gravitational acceleration is common in comets, where it's caused by the rocket effect of outgassing. Jets of vapour shooting out from the sun-warmed surface act like tiny thrusters. But Oumuamua showed no visible signs of outgassing, no dust, no gas, no spectroscopic signatures of any volatile materials, yet something was giving it an extra push, something that would become one of the most debated aspects of this already mysterious object. The precision with which astronomers could track Oumuamua's position was remarkable. By combining observations from multiple telescopes and using sophisticated software to account for the motion of Earth and the effects of parallax, they could determine its position to within a few hundred kilometers, despite it being millions of kilometers away. This precision allowed them to detect the tiny non-gravitational acceleration, a deviation from the expected path of just a few hundred meters over the course of several weeks. It's like watching a car driving down a highway from an airplane and being able to tell that it's drifting slightly to one side by just a few centimeters. Different telescopes contributed different pieces of information to our understanding of Oumuamua. Optical telescopes measured its brightness and color. Infrared telescopes looked for heat radiation that might indicate the composition of its surface. Radio telescopes listened for signals and also attempted radar observations, though Oumuamua was too small and distant for radar to be effective. Each type of observation added constraints on what Oumuamua could and couldn't be. The lack of infrared excess ruled out a large dark object. The absence of radio signals made an active alien probe less likely. The optical observations confirmed the extreme brightness variations that suggested an elongated shape. The observational campaign also revealed the limitations of our current technology. Despite humanity's impressive array of telescopes, ʻOumuamua remained essentially a point of light throughout its visit. We couldn't resolve its shape directly, couldn't determine its composition with certainty, couldn't even be sure of its size. All our conclusions about this object are based on indirect evidence, on the subtle variations in light and position that our instruments could detect. It's a humbling reminder that even with our advanced technology, the universe can present us with mysteries that remain just beyond our ability to fully resolve. As November 2017 progressed, ʻOumuamua grew steadily fainter. The last optical observations were made in early January 2018, when the object had faded to about 27th magnitude, far too faint for all but the largest telescopes to detect. The Hubble Space Telescope made some of the final observations, tracking ʻOumuamua until it was about 5 astronomical units from the Sun, roughly the distance of Jupiter's orbit. After that, our first known interstellar visitor disappeared back into the darkness from which it came, leaving behind only data and questions. The dance of discovery, from the first detection by pan-stars through the intensive global observation campaign to the final fading from view, lasted less than 3 months. In that brief time, humanity got its first confirmed glimpse of an object from another star system. The observations were made possible by decades of technological development, by the dedication of astronomers who spend long nights searching the sky, and by the international cooperation that allows data and resources to be shared rapidly when something important is discovered. ʻOumuamua's visit was brief, but the scientific legacy of those few months of observation will last for generations. Looking back at the discovery, there's something almost serendipitous about the timing. If ʻOumuamua had passed through our solar system just a decade earlier, our survey telescopes might not have been sensitive enough to detect it. If it had approached from a different angle or at a different time of year, it might have been lost in the glare of the sun, or hidden behind the moon during critical observation windows. The fact that we detected it at all, given its small size and rapid motion, suggests that such objects might be passing through our solar system regularly, most of them unseen and unknown. As ʻOumuamua departed our solar system in late 2017 and early 2018, astronomers around the world were carefully tracking its position, plotting each observation point to refine their understanding of its trajectory. It was during this meticulous tracking that something unexpected emerged from the data, a subtle but undeniable deviation from the path that gravity alone should have produced. This discovery would transform ʻOumuamua from merely an interesting interstellar visitor into one of the most puzzling objects ever observed in our solar system, raising questions that challenge our understanding of both natural celestial mechanics and the possibilities of what might exist in the cosmos. The detection of this anomaly required extraordinary precision. Astronomers were measuring the position of an object hundreds of millions of kilometers away, tracking changes in its trajectory that amounted to just a few hundred meters of deviation over several weeks. To appreciate this level of precision, imagine standing in New York and using a telescope to track a golf ball in Los Angeles, and being able to detect if that golf ball moved sideways by the width of a human hair. This is the kind of observational accuracy that modern astronomy has achieved, combining powerful telescopes with sophisticated computer analysis and decades of experience in orbital mechanics. The anomaly itself was a small but persistent acceleration away from the Sun, beyond what could be explained by solar gravity and the gravitational influences of the planets. This extra push was tiny, about 1,000 times weaker than the sun's gravitational pull at Oumuamua's distance. But it was definitely there. Multiple independent teams of astronomers analysed the data using different methods and software, and they all came to the same conclusion. Something other than gravity was affecting ʻOumuamua's motion. The acceleration decreased with distance from the sun, following an inverse square law, which meant that whatever was causing it was somehow related to solar radiation or heating. In our solar system, such non-gravitational accelerations are common in comets. As a comet approaches the sun, solar heating causes frozen gases in its nucleus to sublimate, creating jets of vapor that act like tiny rocket engines. These jets can significantly alter a comet's orbit over time, and astronomers have become quite skilled at modelling and predicting these effects. When the non-gravitational acceleration was first detected in Oumuamua's motion, the natural assumption was that it must be outgassing like a comet, even though no visible signs of such activity had been observed. This presented a profound puzzle. Every comet we've ever observed shows visible signs of outgassing when it exhibits non-gravitational acceleration. The escaping gases carry dust particles with them, creating the characteristic fuzzy coma around the nucleus and often spectacular tails that can stretch for millions of kilometers. Even relatively inactive comets show at least faint signs of dust production when they're close enough to the sun for outgassing to occur. But despite intensive observations with the most sensitive instruments available, including space telescopes that could detect incredibly faint dust clouds, Oumuamua showed absolutely no signs of cometary activity. The absence of detectable outgassing was particularly puzzling, given the magnitude of the acceleration. Based on the observed non-gravitational force, if Oumuamua were outgassing like a normal comet, it should have been producing enough gas and dust to be easily visible to our telescopes. The Spitzer Space Telescope, which is sensitive to infrared radiation that would be emitted by warm dust particles, placed stringent limits on any dust production. The non-detection meant that if Oumuamua was producing dust, it was doing so at levels at least 100 times lower than any comet we've observed with similar non-gravitational acceleration. Scientists began exploring alternative explanations for the mysterious acceleration. One possibility was that Oumuamua might be outgassing pure gases without any dust, something never observed in solar system comets but theoretically possible. Perhaps its surface had been processed by millions of years of cosmic radiation to the point where all the dust had been removed or consolidated, leaving only volatile ices that could sublimate cleanly without carrying dust particles. But even pure gas emission should have been detectable through spectroscopy, and no emission lines were observed in any of the detailed spectroscopic studies. Another hypothesis involved radiation pressure from sunlight. Light carries momentum, and when it reflects off or is absorbed by an object, it imparts a tiny push. For most asteroids and comets, this radiation pressure is negligible compared to their mass. But if Oumuamua were extremely light for its size, perhaps hollow or made of very low-density material, radiation pressure could potentially explain the observed acceleration. This led to one of the most intriguing suggestions about Oumuamua's nature, that it might be a light sail, either natural or artificial. The light sail hypothesis, proposed most prominently by Harvard astronomers Avi Loeb and Shmuel Bialy, suggested that Oumuamua might be a thin sheet of material, perhaps less than a millimeter thick, that was being pushed by solar radiation pressure. If Oumuamua were indeed such a structure, it would need to have an area-to-mass ratio about 10 times higher than any known asteroid or comet. This could explain both the non-gravitational acceleration and the extreme brightness variations that suggested an unusual shape. The idea was controversial, but couldn't be immediately dismissed based on the available data. The possibility of an artificial origin for Oumuamua, while considered unlikely by most astronomers, couldn't be entirely ruled out. If another civilization had developed light sail technology for interstellar travel, something humanity is currently working on with projects like Breakthrough Starshot, then defunct sails might occasionally drift through other star systems. The galaxy could be littered with such technological debris, just as Earth's orbit is increasingly cluttered with defunct satellites. The fact that Oumuamua's velocity relative to the local standard of rest was so low might even suggest it was intended to be found, moving slowly enough that any civilization monitoring their stellar neighborhood would be likely to detect it. More conventional explanations were also explored. Perhaps Oumuamua was made of materials we haven't encountered before in our solar system. Some scientists suggested it might be composed of molecular hydrogen ice, which would sublimate at temperatures where water ice remains frozen and might not produce detectable emissions. Others proposed that it could be a dust bunny, a fractal aggregate of dust particles held together by weak forces with an extremely low density that would make it susceptible to radiation pressure. Each hypothesis had its strengths and weaknesses, and none could fully explain all of Oumuamua's observed properties. The acceleration anomaly also raised questions about Oumuamua's internal structure. If it were outgassing, even invisibly, the jets would create torques that should have changed its rotation rate over time. Comets in our solar system often show such changes, spinning up or slowing down as jets push on different parts of their surface. But Oumuamua's rotation appeared to remain constant throughout the observation period, suggesting either that any outgassing was remarkably symmetric, or that the acceleration was caused by something other than jets. The timing of the acceleration provided another clue. It followed an inverse square law with distance from the Sun, meaning it was strongest when Oumuamua was closest to our star and decreased as it moved away. This is exactly what we would expect from solar heating effects or radiation pressure, but it is also what we might expect from a light sail that was partially reflective and partially absorptive. The acceleration seemed to turn on as Oumuamua approached the Sun and turn off as it departed, almost as if it were designed to give the object a boost as it passed through stellar systems. Some scientists attempted to explain the acceleration through more exotic mechanisms. Perhaps Oumuamua had a highly unusual shape that created asymmetric thermal emission, as it cooled after being heated by the Sun. This Yarkovsky effect, as it's called, can create small accelerations in rotating bodies as they radiate heat, preferentially from their warmer afternoon side. But calculations showed that even with generous assumptions about Oumuamua's thermal properties, the Yarkovsky effect couldn't produce an acceleration as large as what was observed. The mystery deepened when astronomers looked back at Oumuamua's approach to our solar system. If the non-gravitational acceleration had been operating throughout its interstellar journey, powered perhaps by the faint starlight of the galaxy, it would have significantly affected its trajectory over millions of years. But the object's incoming velocity and direction suggested it had been travelling on a relatively straight path, implying that the acceleration only activated when it got close to our Sun. This on-off behaviour is difficult to explain with most natural mechanisms, but might make sense for certain artificial scenarios. the debate over Oumuamua's acceleration became one of the most active areas of research in planetary science. Papers were published proposing new explanations, critiquing existing theories, and calling for more observations of future interstellar objects. The scientific process was playing out in real time, with researchers building on each other's work, finding flaws in proposed explanations, and refining their understanding of what was and wasn't possible. It was a beautiful example of how science grapples with genuine mysteries, not rushing to conclusions, but carefully examining each possibility. The acceleration anomaly also highlighted the importance of continued monitoring of our cosmic neighborhood. If interstellar objects like Oumuamua pass through our solar system regularly, and if they commonly show unexpected behaviors, we need to be ready to study them in greater detail. Several space agencies began considering missions that could intercept future interstellar visitors, using spacecraft already in orbit or rapidly launched, probes that could catch up to these fast-moving objects and study them up close. The European Space Agency's Comet Interceptor mission, planned for launch in the late 2020s, is designed to be able to redirect to an interstellar object if one is discovered with enough warning. As we contemplate this acceleration mystery tonight, it's worth reflecting on how it connects to broader questions about the nature of interstellar space and the objects that traverse it. If Oumuamua's acceleration is due to some previously unknown natural phenomenon, it suggests that the interstellar medium might shape and modify objects in ways we haven't anticipated. Objects, spending millions of years in the near-perfect vacuum between stars, might develop properties unlike anything in our solar system, adapted to an environment we can barely imagine. The acceleration anomaly also raises philosophical questions about how we interpret ambiguous data. When faced with observations that don't fit our existing models, do we stretch those models to accommodate the new data, or do we consider more radical possibilities? The suggestion that Oumuamua might be artificial was met with skepticism by many astronomers, not because the data ruled it out, but because extraordinary claims require extraordinary evidence. Yet the very fact that serious scientists could publish papers in peer-reviewed journals discussing the possibility shows how truly anomalous Oumuamua's behavior was. Consider the implications if Oumuamua's acceleration truly cannot be explained by natural phenomena we understand. It wouldn't necessarily mean the object is artificial, but it would suggest that our understanding of how objects behave in space is incomplete. Perhaps there are forms of matter or physical processes that only manifest under the extreme conditions of interstellar space. Perhaps objects can be shaped by their long journey between stars in ways that produce behaviors we've never seen in our solar system. The acceleration anomaly reminds us that the universe is still full of surprises, even in areas where we thought our understanding was relatively complete. The mystery also connects to questions about the distribution of matter in the galaxy. If objects like Oumuamua are common, and if they commonly show non-gravitational accelerations, then the paths of interstellar objects might be more complex than simple ballistic trajectories. They might be able to surf on stellar radiation, using each close encounter with a star to adjust their course. Over millions of years and many stellar encounters, such objects might develop trajectories that are very different from what we would expect from simple gravitational dynamics. As you lie there tonight, perhaps feeling the gentle pull of sleep beginning to take hold, consider that right now, at this very moment, Oumuamua continues its journey through interstellar space, still carrying its mysteries with it. The acceleration that puzzled astronomers has likely ceased now that it's far from any star, and the object has probably returned to its quiet tumbling through the darkness. But the questions it raised remain very much alive in the minds of scientists around the world, spurring new research, new theories, and new observations. The acceleration anomaly of ʻOumuamua stands as one of the most intriguing puzzles in modern astronomy. It's a reminder that even with all our technology and knowledge, the universe can still surprise us with behaviors we don't expect and can't easily explain. Whether the explanation ultimately proves to be a new natural phenomenon, an exotic form of matter, or something even more extraordinary, the mystery of ʻOumuamua's acceleration has already achieved something important. It has expanded our sense of what's possible in the cosmos, and reminded us that there's still so much we don't know about the universe we inhabit. Throughout human history, we have been casting messages into the cosmos, sometimes intentionally, sometimes not, like children throwing bottles into a vast ocean, hoping someone, somewhere, might find them and understand that they are not alone. These efforts to communicate across the unimaginable distances of space reflect something deep in human nature, a desire to connect, to know that consciousness and intelligence might exist elsewhere in this seemingly infinite universe. As we consider ʻOumuamua tonight, drifting now through the darkness beyond our solar system, we might wonder whether it too could be a message sent by beings we can only imagine, using methods we're just beginning to understand. The idea of interstellar communication has evolved dramatically over the past century. In the early days of radio, Nikola Tesla and Guglielmo Marconi both claimed to have detected signals from Mars, though these were later understood to be natural radio emissions. As our technology improved and our understanding of the cosmos deepened, our attempts at communication became more sophisticated. In 1974, humanity sent its first deliberate message to the stars from the Arecibo radio telescope in Puerto Rico. This message, a simple pattern of ones and zeros that could be decoded to reveal information about human DNA, our solar system, and the telescope itself, was beamed toward the globular cluster M13, some 25,000 light-years away. The Arecibo message was largely symbolic. By the time it reaches its destination, 25,000 years will have passed on Earth, and any reply would take another 25,000 years to return. Civilizations might rise and fall multiple times in such a span. But the message represented something profound. Humanity's first deliberate attempt to announce its presence to the cosmos. Since then, various other radio messages have been sent to nearby stars, each encoding information about Earth and humanity in different ways, each representing our hope that someone might be listening. But radio waves, for all their utility, face fundamental challenges as a means of interstellar communication. They spread out as they travel, becoming weaker with distance according to the inverse square law. A signal that might be easily detectable at the distance of Pluto would be incredibly faint by the time it reached even the nearest star. Radio waves also have to compete with the natural radio emissions of stars, pulsars, and other cosmic phenomena. And perhaps most fundamentally, they require that the receiving civilization be listening at exactly the right frequency, at exactly the right time, pointed in exactly the right direction, a cosmic coincidence that might be vanishingly rare. Physical artifacts, on the other hand, have certain advantages as interstellar messages. They don't degrade with distance the way radio signals do. Once set in motion, They continue travelling through the vacuum of space essentially forever, requiring no power source to maintain their journey. They can carry far more information than any radio signal. Consider that the Voyager Golden Records contain 115 images, greetings in 55 languages, and 90 minutes of music, a cultural payload that would take enormous amounts of time to transmit via radio. And perhaps most importantly, physical artifacts can be discovered by chance, requiring no deliberate search at specific frequencies or times. Humanity has already sent 5 physical artifacts on trajectories that will take them out of our solar system: Pioneer 10 and 11, Voyager 1 and 2, and New Horizons. The Pioneer probes carry plaques showing the figures of a man and woman, our location in the galaxy relative to known pulsars, and a diagram of the hydrogen atom. The Voyager probes carry the famous Golden Records, curated by Carl Sagan and his team, containing sounds and images from Earth. These spacecraft will drift through interstellar space for millions of years, carrying their messages long after humanity itself might have evolved into something unrecognizable or ceased to exist entirely. The Voyager Golden Records are particularly fascinating as an attempt at interstellar communication. They include the sounds of thunder and rain, the calls of birds and whales, human laughter and footsteps. There are images of DNA structure, human anatomy, scenes of daily life from around the world. There's music from Bach to Chuck Berry, from Azerbaijani bagpipes to Peruvian panpipes. The records are a compression of human experience into 90 minutes, an attempt to say, this is who we were, to whoever might find them in the unimaginable future. Instructions for playing the records are etched on their covers in symbolic language that any technologically advanced civilization should be able to decode. But these spacecraft are tiny needles in the cosmic haystack, moving at velocities that, while impressive by human standards, are glacially slow on interstellar scales. Voyager 1, the fastest and most distant of our interstellar emissaries, is travelling at about 17 kilometers per second and won't pass within 2 light years of another star for 40,000 years. The chances of these probes being found by another civilization are almost impossibly small. They are more like monuments to human ambition and hope than practical attempts at communication. Now consider ʻOumuamua in this context. If other civilizations have reached similar conclusions about the challenges of interstellar communication, might they too have chosen to send physical messengers rather than radio signals? The galaxy might be crisscrossed with such artifacts, each carrying information about its creators, their world, their understanding of the universe. Most would pass through stellar systems undetected, but occasionally, like ʻOumuamua, one might be spotted by a civilization that has just developed the technology to detect such visitors. The characteristics of ʻOumuamua are intriguing when viewed through this lens. Its elongated shape, while unusual for a natural object, might make sense for an artificial construct designed to be noticed. A long, thin object produces dramatic brightness variations as it tumbles, making it more likely to catch the attention of astronomical surveys. Its relatively slow velocity with respect to the local standard of rest means it spends more time in each stellar system it passes through, increasing the chances of detection. The mysterious acceleration could be a way of marking the object as unusual, prompting closer investigation by any civilization that observes it. If ʻOumuamua were an intentional message, what might it be trying to communicate? Perhaps the message is simply the object itself, proof that interstellar travel is possible, that objects can survive the journey between stars. Perhaps its trajectory encodes information, with its path through our solar system carefully calculated to demonstrate intelligence through celestial mechanics. Or perhaps, as some have speculated, ʻOumuamua is like a cosmic beacon, designed to be noticed and to prompt the observing civilization to look more carefully for other signs of intelligence in the cosmos. The timing of ʻOumuamua's discovery is also thought-provoking. Humanity has only had the capability to detect such objects for a few decades, and comprehensive sky surveys capable of finding fast-moving faint objects have only been operational for about a decade. If interstellar messengers are passing through our solar system regularly, the fact that we detected one so soon after gaining the ability to do so might suggest they are more common than we imagined. Perhaps every stellar system is regularly visited by such objects, most passing unnoticed until a civilization develops the technology to detect them. There's something poetic about the idea of civilizations separated by vast distances and possibly vast amounts of time, unable to have real-time conversations but still trying to communicate through these drifting messengers. A civilization that sent out ʻOumuamua might have done so millions of years ago, perhaps before humans even evolved. They might be extinct now, their planet a lifeless rock or their star a white dwarf, but their message continues its journey through the cosmos. It's a form of communication that transcends the lifetime of individuals, societies, even species, a truly long-term perspective that our short-lived species struggles to comprehend. The search for extraterrestrial intelligence, SETI, has traditionally focused on radio and optical signals, but ʻOumuamua has prompted a reconsideration of search strategies. Perhaps we should be looking not just for electromagnetic signals, but for physical artifacts passing through our solar system. The Breakthrough Listen project, funded by billionaire Yuri Milner, spent hours pointing radio telescopes at ʻOumuamua, listening for any transmissions. They heard nothing. But the very fact that such observations were made shows how seriously the scientific community takes the possibility of interstellar artifacts as a means of communication. Consider the different philosophies of communication that might exist among hypothetical alien civilizations. Some might favour the immediate but ephemeral nature of radio waves, broadcasting their presence to the cosmos like a shout in the darkness. Others might prefer the permanence of physical artifacts sending out messages that could survive for billions of years. Still others might use methods we haven't even imagined, perhaps encoding information in the arrangement of asteroids in their stellar system, or in the modulation of their star's light, or in gravitational waves that we're only just learning to detect. The challenge of interstellar communication goes beyond just the technical difficulties. There's also the problem of mutual comprehension. How do you communicate with beings whose sensory experience, cognitive processes, and cultural context might be utterly different from your own? The Pioneer plaques and Voyager records assume that the finders will see and hear in ways similar to humans, that they'll understand our mathematical and scientific symbols, that they'll be able to decode our representations of physical objects. But these assumptions might be completely wrong. An alien civilization might perceive the universe through senses we don't possess, might think in ways we can't imagine, might find our attempts at communication as incomprehensible as we might find theirs. This is where physical artifacts might have another advantage. Even if the intended message can't be decoded, the artifact itself conveys information. Its composition tells you about the chemistry and technology of its creators. Its trajectory might reveal something about its origin. Its very existence proves that someone, somewhere, was capable of launching objects into interstellar space. ʻOumuamua, whether natural or artificial, has already communicated something important to us, that objects from other stellar systems can and do visit our cosmic neighbourhood. The idea of ʻOumuamua as a potential message also raises ethical questions. If it were artificial, would we have the right to capture and study it? Would doing so be like opening someone else's mail? These might seem like abstract philosophical questions, but they could become very practical if future interstellar objects show clearer signs of artificial origin. How we choose to interact with potential messages from other civilizations might itself send a message about what kind of species we are. As you lie there in the darkness tonight, perhaps you can imagine the vast network of potential messages crisscrossing the galaxy. Radio waves spreading out from thousands or millions of worlds, carrying news, music, or desperate calls for contact. Physical artifacts drifting between the stars, some launched deliberately as messages, others perhaps just debris from spacefaring civilizations, but all carrying information about their creators. And among them, ʻOumuamua, tumbling through the darkness, its true nature still a mystery, but its effect on human consciousness undeniable. The possibility that ʻOumuamua might be a message, however remote, has already changed us. It has made us think more carefully about how we might communicate with other intelligences, about what kinds of messages might be passing through our solar system unnoticed, about our place in a cosmos that might be filled with other minds trying to make contact. Whether or not ʻOumuamua was intended as a message, it has functioned as one, telling us that we need to look more carefully at the space between the stars, that we need to be ready for discoveries that might challenge our understanding of what's possible. In a sense, every astronomical object is a message, carrying information about the conditions under which it formed, the forces that have shaped it, the journey it has taken. The light from distant stars tells us about their composition and temperature. The orbits of planets reveal the gravitational choreography of their systems. The composition of meteorites speaks of the early solar system's chemistry. ʻOumuamua, as our first confirmed interstellar visitor, carries a message about conditions in another stellar system, about the processes that can eject objects into interstellar space, about the frequency with which such objects might visit us. But there's something special about the idea of an intentional message, something that speaks to our deep need for connection and meaning. The universe often seems cold and indifferent, its vast spaces empty and hostile to life. The possibility that someone, somewhere, might be trying to communicate, might be saying, "You are not alone," transforms that cold cosmos into a place of potential fellowship. Even if ʻOumuamua is just a rock, the fact that we can seriously consider it might be something more shows how far we've come in our cosmic perspective. Among all the explanations proposed for ʻOumuamua's peculiar characteristics, perhaps none has captured the imagination quite like the light sail hypothesis. This idea, proposed most prominently by Harvard astronomer Avi Loeb and his colleague Shmuel Bialy, suggests that ʻOumuamua might be an artificial structure designed to be propelled by radiation pressure from stars. It's a hypothesis that bridges the gap between current human technology and speculative alien engineering, between what we're beginning to build ourselves and what others might have built long ago. As we explore this possibility tonight, we're not just considering ʻOumuamua, but also contemplating the future of interstellar travel and the kinds of artifacts that spacefaring civilizations might scatter throughout the galaxy. The concept of light sails, also known as solar sails or photon sails, is not science fiction but established physics that humanity is already beginning to implement. Light, despite having no mass, carries momentum. When photons strike a surface and are absorbed or reflected, they transfer this momentum to the object, creating a tiny but persistent push. It's the same pressure that causes comet tails to always point away from the sun, regardless of the comet's direction of motion. For most objects in space, this radiation pressure is negligible compared to gravity, but for something with a large surface area and very small mass, like a thin reflective sail, it can become the dominant force. The Japanese space agency JAXA successfully demonstrated this technology with their KAROS spacecraft in 2010, deploying a 14-meter wide sail that used solar radiation pressure to navigate through space. The Planetary Society's Light Sail 2, launched in 2019, has been using a 32 square meter sail to raise its orbit around Earth, proving that light sail technology works and can be controlled. These early demonstrations are primitive compared to what might be possible with more advanced materials and designs, but they prove the fundamental concept. You can sail on light itself, using no fuel, just the endless stream of photons from stars. For interstellar travel, light sails offer unique advantages. Traditional rockets are limited by the tyranny of the rocket equation. To go faster, you need more fuel, but that fuel adds mass, which requires even more fuel to accelerate. This vicious cycle makes it essentially impossible to reach the speeds necessary for interstellar travel using conventional propulsion. But a light sail carries no fuel. Once deployed, it can accelerate continuously as long as it's exposed to light, eventually reaching velocities that could make travel to nearby stars feasible within decades or centuries rather than tens of thousands of years. The Breakthrough Starshot project, announced in 2016 and funded by Yuri Milner with support from Stephen Hawking and others, aims to demonstrate the potential of light sails for interstellar travel. The concept involves using powerful lasers on Earth to accelerate tiny spacecraft equipped with light sails to about 20% of the speed of light. At such velocities, these starships could reach Proxima Centauri, our nearest stellar neighbour, in about 20 years. It's an audacious plan that faces enormous technical challenges, but it represents humanity's first serious attempt to design a mission that could reach another star within a human lifetime. Now consider ʻOumuamua through the lens of light sail technology. For the observed non-gravitational acceleration to be explained by radiation pressure, ʻOumuamua would need to have an area-to-mass ratio about 10 times higher than any known asteroid or comet. This would require it to be extraordinarily thin, perhaps less than a millimeter thick, while maintaining structural integrity during its tumbling motion and close approach to our Sun. Such a structure seems impossible for a natural object, but might be exactly what we'd expect from an artificial light sail. The mathematics of the light sail hypothesis are compelling in their simplicity. Given ʻOumuamua's observed acceleration and the intensity of sunlight at its distance from the Sun, Loeb and Bialy calculated that it would need an area-to-mass ratio of about 0.1 square meters per gram. For comparison, the sails being designed for Breakthrough Starshot would have similar ratios. If ʻOumuamua were a square sail about 20 meters on each side and less than a millimeter thick, made of material with a density similar to aluminum, it would have approximately the right characteristics to explain the observed acceleration. But why would an alien light sail be tumbling through our solar system? Several scenarios have been proposed. Perhaps it's a piece of debris from an alien breakthrough starshot-like project, a sail that malfunctioned or completed its mission and is now drifting derelict through space. Given that we're planning to launch thousands of such sails toward nearby stars, it's not unreasonable to imagine that other civilizations might have done the same, filling the galaxy with spent sails like maritime flotsam drifting on cosmic currents. Another possibility is that ʻOumuamua might be a functional probe, still operating but in a passive mode. Its tumbling motion might be intentional, allowing it to scan its surroundings in all directions as it rotates. The acceleration from solar radiation might be part of its design, allowing it to gain velocity boosts as it passes through stellar systems without requiring onboard fuel. Such a probe might be one of millions or billions sent out by an advanced civilization to survey the galaxy, gathering data about stellar systems and potentially habitable planets. The light sail hypothesis also offers an explanation for ʻOumuamua's unusual shape. If it's a sail, it would naturally be flat and thin, which could produce the extreme brightness variations observed as it tumbles. The reddish colour might be due to the sail material itself, or to coatings designed to protect it from cosmic radiation during its long interstellar journey. The lack of observable outgassing makes perfect sense if ʻOumuamua is artificial. There will be no volatile materials to sublimate, no dust to be released. Critics of the light sail hypothesis point out several challenges. First, the tumbling motion seems problematic for a functional sail, as it would make controlled navigation difficult. However, this assumes the sail is currently operational. If it's derelict or in a passive observation mode, tumbling might not be an issue. Second, no radio emissions or other signs of technology were detected from ʻOumuamua. But an alien probe might use communication methods we can't detect, or it might be designed to remain silent unless triggered by specific conditions. The survival of such a thin structure during its interstellar journey and close solar approach is another concern. Interstellar space is not perfectly empty. There are dust grains, cosmic rays, and atoms of gas that would gradually erode any thin sail over millions of years. However, advanced materials we can barely imagine might be far more durable than anything we can currently produce. Carbon nanotubes, graphene, or exotic metamaterials might allow the construction of sails that could survive interstellar journeys while remaining incredibly thin and light. If ʻOumuamua is a light sail, what does this tell us about its creators? They would need to be a spacefaring civilization with advanced material science and a long-term perspective on exploration. They might be using light sails as a low-cost way to explore the galaxy, launching millions or billions of them, knowing that only a tiny fraction might encounter interesting stellar systems. It's a strategy that makes sense for a patient civilization thinking on timescales of millions of years rather than human lifetimes. The implications of the light sail hypothesis extend beyond just ʻOumuamua. If one civilization has filled the galaxy with light sails, others might have done the same. The galaxy could be permeated with artificial structures, most too small or distant for us to detect, occasionally passing through stellar systems like cosmic messages in bottles. This would fundamentally change our understanding of the interstellar medium, transforming it from a nearly empty void to a space potentially rich with artifacts of intelligent origin. The light sail hypothesis has also influenced how we think about future observations. If interstellar objects like ʻOumuamua are sometimes artificial, we need to be prepared to recognize the signs. This might mean looking for specific area-to-mass ratios, unusual reflective properties, or trajectories that seem optimized for gathering information about stellar systems. The Legacy Survey of Space and Time, to be conducted by the Vera Rubin Observatory starting in the mid-2020s, is expected to detect many more interstellar objects. Each one will be an opportunity to test the predictions of the light sail hypothesis and other theories about Oumuamua's nature. As we contemplate the possibility that Oumuamua might be a light sail, we're also contemplating our own future as a spacefaring species. The same technology that might explain Oumuamua's acceleration is technology we're developing ourselves. In a sense, Oumuamua might be showing us our own future, a time when human-made light sails traverse the galaxy, carrying our robots, our messages, perhaps even our descendants to the stars. The object that puzzled us in 2017 might be a preview of what will become, a glimpse of the kind of artifacts we'll scatter through the cosmos. The beauty of the light sail hypothesis is that it's testable. As we detect more interstellar objects, we can look for patterns, do some show acceleration consistent with radiation pressure. Do they have the extreme shapes we might expect from artificial structures? Are their trajectories optimized for surveying stellar systems? Each new discovery will add data points, gradually building a picture of whether artificial objects are mixed among the natural population of interstellar visitors. Tonight, as you drift towards sleep, imagine Oumuamua as a sail, its surface catching starlight as it tumbles through the darkness. Perhaps it was launched millions of years ago by beings we can't imagine, on a mission we can't fathom, using principles we're just beginning to understand. Or perhaps it's something else entirely, a natural phenomenon that happens to mimic what we expect from our own future technology. Either possibility is profound. Either we've detected our first artificial interstellar object, or nature has created something so unusual that it's expanded our understanding of what's possible in the cosmos. The light sail hypothesis represents something important in the scientific process, the willingness to consider unconventional explanations when conventional ones fall short. It's not wild speculation but careful calculation based on observed properties and known physics. Whether or not Oumuamua is a light sail, the fact that serious scientists can propose and defend this hypothesis in peer-reviewed journals shows how mysterious this object truly is, and how open we must be to unexpected discoveries as we explore the universe. Yet as we drift deeper into contemplation tonight, we must also hold space for the possibility that Oumuamua, for all its strangeness, might be entirely natural, a cosmic wonder born not from intelligence, but from the extraordinary processes that shape matter in the vast spaces between stars. The universe, after all, has repeatedly shown us that nature herself is capable of creating phenomena that seem impossible until we understand the physics behind them. Perhaps Oumuamua is teaching us not about alien civilizations, but about the remarkable things that can happen to matter during millions of years of interstellar travel, about forms of cosmic ice we've never encountered, about the ways that the extreme environment between stars can sculpt and transform ordinary materials into something extraordinary. Consider for a moment the journey that any natural interstellar object must undertake. It begins in the chaos of a forming stellar system, where planets are still coalescing from dust and gas, where gravitational interactions can be violent enough to fling smaller bodies completely out of their birth system. The object that would become Oumuamua might have formed billions of years ago in the disk around a young star. Perhaps a star very different from our Sun. It might have spent millions of years orbiting peacefully before a close encounter with a forming gas giant planet gravitationally catapulted it into interstellar space, sending it on a journey that would last longer than complex life has existed on Earth. Once in interstellar space, the object enters an environment unlike anything in our solar system. The temperature drops to just a few degrees above absolute zero. The pressure becomes so low that it's essentially a perfect vacuum, better than anything we can create in laboratories on Earth. Cosmic rays, high-energy particles from distant supernovae and other violent cosmic events, bombard the object constantly, gradually altering its surface chemistry. The faint light from distant stars provides the only energy, barely enough to warm the object above the cosmic microwave background temperature. In this extreme environment, matter might behave in ways we've never observed, forming structures and compositions that don't exist in the relatively warm, dense environment of our solar system. One of the most intriguing natural explanations for Oumuamua involves exotic forms of ice that might exist only in interstellar space. Scientists have proposed that Oumuamua might be made of molecular hydrogen ice, a substance that would be impossible in our solar system, but might form in the coldest regions of giant molecular clouds where stars are born. Molecular hydrogen ice would sublimate at temperatures where water ice and other common volatiles remain frozen, potentially explaining why Oumuamua showed acceleration without visible outgassing. The hydrogen gas released would be nearly impossible to detect with our current instruments, transparent and colourless, leaving no trace except the mysterious push it provided. The formation of a molecular hydrogen ice object would require extraordinary conditions. In the dense cores of molecular clouds, where temperatures can drop to just 10 degrees above absolute zero, hydrogen molecules might condense onto dust grains, gradually building up layers of this exotic ice. If a chunk of this material were somehow ejected into interstellar space before the warming influence of a forming star could sublimate it, it might survive for millions of years, protected by the very coldness of the void. When it finally encountered our Sun, the gentle warming would cause the hydrogen to sublimate from within, creating invisible jets that could explain the observed acceleration. Another fascinating possibility is that Oumuamua might be a fragment of a nitrogen ice world, similar to Pluto but from another stellar system. In our outer solar system, we've discovered that nitrogen ice is common on bodies like Pluto and Triton, forming vast plains and glaciers. If a collision or gravitational interaction shattered such a world in another system, fragments of nearly pure nitrogen ice might be ejected into interstellar space. Like molecular hydrogen, nitrogen ice would sublimate at relatively low temperatures and might not produce the dust we associate with cometary activity. The reddish colour could come from organic compounds formed by cosmic ray irradiation of the nitrogen ice surface over millions of years. The shape of Oumuamua presents its own natural mystery. That extreme elongation, if real, is unlike anything we see among the asteroids and comets of our solar system. But perhaps the very process of interstellar travel could create such shapes. One theory suggests that Oumuamua might have been carved by millions of years of erosion from interstellar dust and gas. Though the interstellar medium is incredibly sparse, over vast timescales, even the gentle erosion of individual atoms and dust grains could sculpt an object. If the erosion were directional, perhaps due to the object's motion through space or its rotation, It might preferentially remove material from certain faces, gradually creating an elongated shape like a cosmic sculpture carved by time itself. There's also the possibility that ʻOumuamua is what scientists call a fractal aggregate, essentially a cosmic dust bunny. In the microgravity environment of space, dust particles can stick together through weak van der Waals forces, creating structures that are mostly empty space. Such objects can have bizarre properties, with densities so low they would float in Earth's atmosphere if they could somehow maintain their structure. A fractal aggregate might have the very low mass-to-area ratio needed to be accelerated by solar radiation pressure, while its porous structure could explain why it didn't break apart during its close approach to the Sun. The tumbling motion might have helped it maintain structural integrity, like a slowly rotating ball of cotton candy. The idea of ʻOumuamua as a fractal aggregate connects to broader questions about how matter behaves in the absence of strong gravitational fields. In our solar system, most objects are either solid bodies held together by their own gravity and material strength, or rubble piles loosely bound by weak gravity. But in interstellar space, where objects can drift for millions of years without significant gravitational influences, matter might assemble itself in ways we haven't imagined. Electrostatic forces, magnetic fields, and van der Waals interactions might become dominant, creating structures that would be impossible in the gravity wells of stellar systems. Some scientists have proposed that ʻOumuamua might be a fragment of a disrupted planet's core, perhaps made of materials we rarely see on the surfaces of solar system objects. If a rocky planet in another system were torn apart by tidal forces or a catastrophic collision, fragments of its deep interior might be ejected into space. These fragments could have compositions unlike anything we've studied, perhaps rich in metals or exotic minerals formed under extreme pressure. The acceleration might be caused by phase transitions in these materials as they were heated by the sun, releasing trapped gases or causing structural changes that created thrust. The cosmic ray processing that ʻOumuamua experienced during its interstellar journey might have created a unique surface layer with properties we don't fully understand. When high-energy particles strike a surface in the vacuum of space, they can create a thin layer of modified material, darker, redder, and chemically different from the interior. This space weathering, as it's called, is observed on asteroids and airless moons in our solar system, but the effect might be much more extreme on objects that have spent millions of years in interstellar space. The processed layer might act as an insulating blanket, allowing volatile materials beneath to survive until solar heating penetrates deep enough to cause sublimation. Consider too the possibility that ʻOumuamua represents a type of object that forms specifically in the environments around dying stars. When stars like our Sun reach the end of their lives, they expel their outer layers, creating planetary nebulae filled with hot gas and dust. In these extreme environments, with intense radiation and stellar winds, matter might condense in unusual ways. Perhaps ʻOumuamua is a stellar fossil, a remnant of processes that occurred as its parent star died, carrying information about stellar death and rebirth across the galaxy. The natural explanation for ʻOumuamua also raises fascinating questions about the population of interstellar objects. If objects like ʻOumuamua are natural, then every stellar system must be losing material to interstellar space, and the galaxy must be filled with trillions upon trillions of such objects. They would represent a previously unknown component of the galactic ecosystem, carrying material from system to system, potentially even carrying organic molecules or the building blocks of life. The galaxy becomes not a collection of isolated stellar islands, but an interconnected web with material constantly flowing between systems. Recent observations of young stellar systems by telescopes like ALMA, Atacama Large Millimeter Array, have shown that planet formation is often a violent process, with evidence of massive collisions and orbital disruptions. These events could easily eject large amounts of material into interstellar space. If this is common, then objects like ʻOumuamua might preserve information about the early stages of planetary system formation. Frozen in time during their long interstellar journeys, each interstellar visitor would be like a core sample from another system's history, carrying clues about how planets form and evolve. The study of ʻOumuamua has also led scientists to reconsider what they know about our own solar system's small bodies. Perhaps some of the objects we've assumed are native to our solar system are actually captured interstellar visitors. The asteroid 514107, ʻOumuamua, for instance, orbits the Sun backward compared to the planets, and has characteristics suggesting it might have been captured from interstellar space billions of years ago. If this is true, we might have samples of interstellar material already in our cosmic backyard, waiting to be studied. The possibility that ʻOumuamua is natural but exotic has important implications for future space exploration. If interstellar objects commonly have compositions or structures unlike anything in our solar system, studying them could revolutionize our understanding of planetary science and cosmochemistry. Missions to intercept future interstellar visitors would be like traveling to another stellar system without the need for decades or centuries of travel. Each object would be a natural probe from another star, delivered to our doorstep by the patient dynamics of galactic motion. As you lie there tonight, perhaps feeling the gentle weight of sleep beginning to settle upon you, consider the profound beauty of either possibility. If ʻOumuamua is natural, it tells us that the universe is even more creative and diverse than we imagined, that the spaces between stars are laboratories where exotic forms of matter can exist and evolve. The cosmos becomes not empty void, but a realm of endless possibility, where the extreme conditions create phenomena we're only beginning to discover. The debate over ʻOumuamua's nature, artificial or natural, is in many ways a false dichotomy. The truth might be something we haven't imagined, a phenomenon that doesn't fit neatly into our categories. Perhaps there are natural processes that create objects that look artificial by our standards, or perhaps the distinction between natural and artificial is not always clear-cut. Artificial becomes meaningless when considering civilizations that might engineer matter at the molecular level. ʻOumuamua challenges us to keep our minds open, to be prepared for discoveries that don't fit our preconceptions. The search for a natural explanation for ʻOumuamua has already advanced our understanding of what's possible in the universe. Scientists have had to think creatively about exotic ices, unusual formation mechanisms, and the effects of interstellar travel on matter. Each proposed explanation, even if ultimately proven wrong, expands our theoretical framework and prepares us for future discoveries. This is how science progresses, not always through finding the right answer immediately, but through the process of exploring possibilities and gradually narrowing down what's possible. Tonight, as we contemplate these natural wonders, we're reminded that the universe doesn't need intelligence to create mystery and beauty. The simple interaction of matter and energy, played out over cosmic timescales in extreme environments, can produce phenomena that challenge our understanding and expand our sense of wonder. ʻOumuamua, whether a nitrogen ice fragment, a hydrogen iceberg, or something we haven't yet imagined, is a reminder that nature herself is the ultimate artist, sculpting matter into forms we're only beginning to appreciate. As we move deeper into the quiet hours of night, let us pull back from the specific mysteries of ʻOumuamua and consider what this visitor means for our understanding of our place in the cosmos. ʻOumuamua travelled for perhaps millions of years before briefly visiting our solar system, its journey connecting us to distant stars and to vast scales of time that dwarf human experience. In October 2017, when this interstellar messenger passed through our cosmic neighbourhood, it marked not just a scientific discovery, but a moment of profound philosophical importance. Humanity's first confirmed encounter with an object from another star system, a tangible link to the galaxy beyond our sun's influence. To truly appreciate the significance of ʻOumuamua's journey, we must first grapple with the almost incomprehensible scales of interstellar space and time. Our solar system, vast as it seems with its distant planets and far-flung comets, is just a tiny bubble in an ocean of emptiness. The nearest star to our Sun, Proxima Centauri, lies about 4.2 light-years away, a distance so vast that light itself, the fastest thing in the universe, takes over 4 years to make the journey. If we could shrink the solar system down so that Earth's orbit was just 1 meter across, Proxima Centauri would still be over 270 kilometers away. In this scaled model, ʻOumuamua would be smaller than a speck of dust, invisible to the naked eye, drifting across those hundreds of kilometers of emptiness. The trajectory analysis of ʻOumuamua suggests it came from the general direction of the constellation Lyra, though not from any specific star we can identify. This is because over the millions of years of ʻOumuamua's journey, the stars themselves have moved significantly. Our Sun orbits the centre of the Milky Way galaxy at about 230 kilometers per second, completing 1 galactic year every 230 million Earth years. Other stars have their own orbits, their own velocities, creating a slow cosmic dance where stellar positions shift dramatically over geological timescales. The star that gave birth to ʻOumuamua might now be on the opposite side of the galaxy, or it might have died, exploding as a supernova or fading as a white dwarf. This temporal disconnect between ʻOumuamua and its origin point speaks to something profound about interstellar communication and contact. If ʻOumuamua were a deliberate message, its senders couldn't know where or when it would be received. They would be casting their message into the future as much as into space, trusting that somewhere, somewhen, a civilization might develop the technology to detect and interpret it. It's a form of communication that requires thinking on timescales far beyond individual lives, beyond civilizations, perhaps beyond species themselves. The beings that might have sent ʻOumuamua could be extinct, evolved into something unrecognizable, or transcended physical existence entirely by the time their message was received. The discovery of ʻOumuamua has forced us to reconsider the interconnectedness of stellar systems. We've long thought of stars and their planets as isolated islands in space, separated by vast voids that nothing could cross. But ʻOumuamua proves that material does flow between these islands, that stellar systems can exchange matter across the light years. This exchange might be rare from the perspective of a human lifetime, but on cosmic timescales, it could be quite common. Current estimates, based on the detection of ʻOumuamua and the volume of space we monitor, suggest that several interstellar objects pass through the inner solar system each year, most too small or faint for us to detect. If these estimates are correct, then over the 4.6 billion year history of our solar system, Earth has been visited by billions of interstellar objects. Some might have impacted our planet, delivering exotic materials or perhaps even organic molecules from other stellar systems. The idea of panspermia, that life might spread between worlds via meteorites or comets, takes on new relevance in light of ʻOumuamua. If objects regularly travel between stellar systems, and if they can preserve organic molecules or even microbial life during these journeys, then life might not arise independently on each habitable world, but might spread through the galaxy like seeds on a cosmic wind. Consider what this means for our understanding of life on Earth. Every organism on our planet, from the simplest bacteria to the most complex mammals, shares a common biochemistry based on DNA, RNA, and proteins. This suggests all Earth life descended from a common ancestor, but what if that ancestor itself came from elsewhere? What if life on Earth began with organic molecules or primitive organisms delivered by an interstellar visitor like ʻOumuamua billions of years ago? We might all be aliens, descendants of interstellar travellers, connected to life that might exist around distant stars. The cosmic perspective that ʻOumuamua provides extends beyond just biology to our understanding of planetary formation and evolution. Every element heavier than hydrogen and helium was forged in the nuclear furnaces of stars or in the violent explosions of supernovae. The carbon in our bodies, the oxygen we breathe, the silicon in Earth's rocks, all were created in stars that lived and died before our sun was born. These elements were dispersed into space and eventually incorporated into the nebula that gave birth to our solar system. But ʻOumuamua reminds us that this process of stellar recycling might not be confined to local regions of space. Elements forged in stars across the galaxy might be transported between stellar systems by interstellar objects, creating a form of galactic metabolism where matter is constantly processed and reprocessed, shared and recycled. The brief visit of ʻOumuamua, just a few months from detection to disappearance, highlights the fleeting nature of cosmic encounters. In the vast scales of space and time, the window for two objects to interact is vanishingly small. Earth and ʻOumuamua, both following their respective paths through space, happen to be in the same region at the same time for just a cosmic instant. A few months earlier or later, and we would have missed it entirely. This temporal coincidence makes us wonder how many other interstellar visitors have passed by unnoticed, carrying their secrets through our solar system, while humanity was still learning to use fire, or while dinosaurs roamed the Earth. The detection of ʻOumuamua also marks a threshold moment in human technological and scientific development. For most of our species' existence, we've been unable to detect such objects. Even a century ago, ʻOumuamua would have passed through completely unnoticed. It's only in the last few decades that we've developed the telescopes and computational tools necessary to spot and track fast-moving faint objects. In a sense, ʻOumuamua arrived at just the right time, when we were finally ready to see it. This timing might be coincidence, or it might reflect something deeper about the development of technological civilizations and their ability to detect interstellar visitors. From a cosmic perspective, the mystery of ʻOumuamua's nature whether natural or artificial, becomes less important than what it represents. It's proof that our solar system is not isolated, that we're part of a larger galactic community where matter and perhaps information flow between stellar systems. Whether ʻOumuamua is a simple rock or an alien artifact, it connects us to the galaxy in a tangible way. We've touched, however briefly and distantly, something from another star. We've observed an object that has travelled through realms we can barely imagine, that has witnessed cosmic vistas we'll never see, that carries in its composition and trajectory information about parts of the galaxy we may never directly explore. The philosophical implications of ʻOumuamua extend to questions about uniqueness and commonality in the universe. If ʻOumuamua is natural, it suggests that the processes that shape matter are universal, that the same physics that operates in our solar system operates everywhere. But it also suggests that these universal processes can create things we've never seen before, that the universe's creativity exceeds our imagination. If ʻOumuamua is artificial, it suggests we're not alone, that intelligence and technology might be common in the galaxy. Either possibility fundamentally changes our cosmic perspective, moving us from cosmic isolation to cosmic participation. ʻOumuamua has also changed how we think about the future of space exploration. Traditional thinking about interstellar travel focuses on sending spacecraft from Earth to other stars, journeys that would take decades, centuries, or millennia. But ʻOumuamua suggests another possibility, that interesting samples from other stellar systems come to us. Instead of travelling to other stars, we might be able to study them by intercepting and analysing interstellar visitors. Each object would be a natural sample return mission, delivering material from distant stellar systems to our cosmic doorstep. The European Space Agency's Comet Interceptor mission, planned for launch in the late 2020s, represents humanity's first attempt to be ready for such opportunities. The spacecraft will wait at a stable point in space, ready to redirect to intercept an interesting comet or, if we're lucky, another interstellar visitor. Future missions might include spacecraft specifically designed to chase down and study interstellar objects, perhaps even returning samples to Earth. In this way, ʻOumuamua has opened a new chapter in space exploration, one where we don't just explore our own solar system, but sample the galaxy itself. As we contemplate ʻOumuamua from our cosmic perspective, we're reminded of Carl Sagan's famous pale blue dot reflection. Earth is a mote of dust suspended in a sunbeam, a tiny world in a vast cosmos. But ʻOumuamua adds another dimension to this perspective. We're not just small, we're also connected. We're part of a galaxy where objects travel between stars, where matter is shared across light years, where the atoms in our bodies might have originated in stellar systems we'll never see. The cosmic perspective that ʻOumuamua provides is one of both humility and connection, reminding us that we're participants in a galactic story that began billions of years before Earth formed and will continue billions of years after it's gone. The way humanity responded to ʻOumuamua also reveals something important about our species at this moment in our development. Within days of its discovery, telescopes around the world were coordinated to observe it. Scientists from different countries, cultures, and backgrounds worked together to understand it. The data was shared freely, the analyses were published openly, the debates were conducted publicly. In our response to ʻOumuamua, we see humanity at its best, curious, collaborative, and capable of transcending our terrestrial divisions when faced with a cosmic mystery. This global scientific collaboration in studying ʻOumuamua might itself be a kind of message to the cosmos. If other intelligences exist and are somehow monitoring our response to interstellar visitors, they would see a species just beginning to develop the technology to detect such objects, eagerly studying them with every tool at our disposal, openly sharing our findings, and seriously considering even unlikely possibilities about their nature. They would see a young technological civilization taking its first steps toward cosmic awareness, ready to engage with the mysteries of the universe, even when those mysteries challenge our preconceptions. The cosmic perspective also helps us appreciate the privilege of living at this particular moment in history. We're among the first humans to know with certainty that objects from other star systems visit our solar system. We're part of the generation that discovered the first confirmed interstellar visitor. Our children and grandchildren will grow up in a world where this is accepted fact, where the connection between stellar systems is taken for granted. But we lived through the transition, the moment when humanity's view of its cosmic neighborhood fundamentally changed. As you drift deeper into the peaceful realm of sleep tonight, carry with you this cosmic perspective that ʻOumuamua has given us. You are made of star stuff, as Carl Sagan said, atoms forged in stellar furnaces across the galaxy. You live on a small world orbiting an ordinary star, one of hundreds of billions in our galaxy. And now you know that this small world is occasionally visited by messengers from other stars, objects that have travelled for millions of years across the vast darkness to briefly pass through our neighbourhood. Whether ʻOumuamua was a simple rock or something more extraordinary, it has connected us to the cosmos in a new way, reminding us that we're not isolated but part of a vast, dynamic, interconnected galaxy, where the impossible journey between stars has already been accomplished, at least by one small, mysterious object that we were privileged to glimpse in 2017. By the time humanity recognized ʻOumuamua's interstellar nature, it was already leaving us behind, racing away at speeds that no current spacecraft could match. Our telescopes caught only glimpses. Our instruments gathered only fragments of data, like trying to understand a whole novel from a few random pages glimpsed as they blow past in the wind. This frustrating limitation, discovering something extraordinary just as it's disappearing forever, raises profound questions about what else we might have missed, not just about ʻOumuamua itself, but about the countless other interstellar visitors that must have passed through our solar system unnoticed throughout history. Tonight, as we explore these missed opportunities and hidden possibilities, we enter a realm of cosmic what-ifs that speaks to both the limitations of our current technology and the tantalizing possibilities that await us as our capabilities improve. The timing of ʻOumuamua's discovery was particularly cruel in its irony. When Robert Weryk first identified it in the Pan-STARRS data on October 19, 2017, the object had already made its closest approach to the Sun 6 weeks earlier. It had passed closest to Earth 5 days before discovery. By the time the astronomical community fully understood what they were looking at, the first confirmed interstellar visitor, ʻOumuamua, was already 33 million kilometers from Earth and rapidly receding. Every day that passed, it grew fainter and more difficult to study. It was like discovering a unicorn in your garden just as it was leaping over the fence, never to return. The observations we did manage to collect were remarkable given the circumstances, but they represent only a tiny fraction of what we could have learned with more time. We never got a resolved image of ʻOumuamua. It remained a point of light in even our most powerful telescopes. Its shape, that extraordinary elongation suggested by the brightness variations, is inferred rather than directly observed. We don't know if it's cigar-shaped or pancake-flat, smooth or rough, solid or porous. The most basic questions about its physical structure remain unanswered, and now, with ʻOumuamua beyond the reach of our instruments, they will remain unanswered forever. Consider what we might have learned if we had discovered ʻOumuamua earlier in its approach. If we had spotted it a year before its closest approach, we would have had time to plan a comprehensive observation campaign. Space telescopes could have been programmed for extended observations. Radio telescopes could have attempted radar imaging as it passed Earth. We might have even had time to redirect existing spacecraft or launch a dedicated mission to intercept it. The Japanese space agency JAXA has shown that their Hayabusa 2 spacecraft could have been redirected to intercept ʻOumuamua if it had been discovered just a few months earlier. The opportunity to study an interstellar object up close, perhaps even to collect samples, was there. We just missed it by a matter of weeks. The spectroscopic data we collected on ʻOumuamua was limited by its faintness and the short observation window. Spectroscopy, which analyzes the wavelengths of light reflected or emitted by an object, can reveal its composition, but it requires collecting enough light to create a detailed spectrum. With ʻOumuamua, we got only basic colour information and rough spectral characteristics. We know it's reddish and doesn't show obvious signs of water ice or common minerals, but the detailed composition remains a mystery. There could be exotic materials on its surface, complex organic molecules, or even technological signatures that our limited spectra simply couldn't detect. One of the most tantalizing missed opportunities involves the search for artificial signals from ʻOumuamua. The Breakthrough Listen project did point radio telescopes at the object, listening for transmissions across a wide range of frequencies. But these observations were necessarily limited. ʻOumuamua was already distant and faint, and we could only listen for a few hours. If the object were transmitting intermittently, or at frequencies we didn't check, or using a technology we don't recognize as communication, we would have missed it. The absence of detected signals doesn't mean there were no signals to detect, only that we didn't detect them in our limited search. But the story of what we might have missed extends far beyond just ʻOumuamua itself. If current estimates are correct, and several interstellar objects pass through the inner solar system each year, then thousands have passed through during the era of modern astronomy. How many of these did we miss because they were too faint, or because they passed through parts of the sky we weren't monitoring, or because they moved too quickly for our automated detection systems to flag them? Each of these missed visitors was a lost opportunity to study material from another star system, to test our theories about planetary formation, to search for signs of life or intelligence beyond Earth. Looking back through historical astronomical records, there are tantalizing hints that might not have been our first interstellar visitor, just our first confirmed one. Some astronomers have suggested that certain unusual comets observed in the past might have been interstellar objects that we misidentified. Comet C/1980E, One Bowel, for instance, had an orbit that took it out of the solar system after its discovery, and its trajectory suggested it might have been barely bound to the Sun. With the less precise measurements available in 1980, we couldn't determine whether it was truly interstellar or just on a very long elliptical orbit. How many other ʻOumuamuas have we catalogued as unusual comets or asteroids, not recognizing their true nature? The possibility that we've been missing interstellar objects for decades or centuries raises questions about what might be hiding in our existing astronomical data. Modern astronomers are now going back through archived observations, looking for objects that might have been interstellar visitors. This data mining has already yielded interesting candidates. Some objects previously classified as long-period comets show orbital characteristics that suggest they might have been interstellar. The improved orbital calculations possible with modern computers and methods might reveal that we've been visited before, we just didn't realize it. There's something particularly poignant about the possibility that Earth has been regularly visited by interstellar objects throughout human history, but we've only just developed the ability to recognize them. Imagine all the ʻOumuamuas that passed through while ancient astronomers watched the skies, seeing only the fixed stars and wandering planets they could observe with the naked eye. Think of all the interstellar visitors that arrived during the Age of Exploration, when humans were discovering new continents on Earth, but remained blind to these visitors from other star systems. Consider the cosmic irony that while we spent centuries wondering if we were alone in the universe, evidence of our cosmic connections might have been passing through our solar system regularly, unseen and unrecognized. The question of what we might have missed becomes even more intriguing when we consider the possibility that some interstellar objects might have been deliberately targeted at our solar system. If an alien civilization wanted to study stellar systems throughout the galaxy, they might send probes designed to be discovered by any civilization that reached a certain level of technological development. These probes might be programmed to arrive when a system's planets were in particular configurations, or when the target civilization was likely to have developed astronomy. Did we miss such a probe by decades or centuries? Is there an interstellar artifact sitting in the outer solar system right now, waiting to be discovered, having arrived too early for us to detect it during its active phase? The physical characteristics of ʻOumuamua that we did observe raise questions about what unusual features we might have missed. The extreme brightness variations suggested an elongated shape. But what if the reality is even stranger? Perhaps ʻOumuamua has a complex artificial structure that we couldn't resolve. Perhaps it's covered in symbols or patterns that encode information, like a cosmic Rosetta Stone that we glimpsed but couldn't read. Perhaps its surface chemistry contains clear biosignatures or technosignatures that our limited spectroscopy couldn't detect. The data we collected rules out many possibilities but leaves many others open. One of the most significant things we might have missed is the opportunity to understand ʻOumuamua's acceleration mechanism. If we had discovered it earlier and tracked it through its entire passage through the inner solar system, we might have been able to determine whether the acceleration was constant or variable, whether it depended on solar radiation or temperature, whether it was aligned with the object's rotation or independent of it. These details could have definitively answered whether the acceleration was due to outgassing, radiation pressure, or something else entirely. Instead, we're left with models and speculation based on incomplete data. The missed opportunity to study ʻOumuamua in detail has implications for our understanding of planetary system formation. Every stellar system has its own unique history, its own chemical composition based on the nebula from which it formed, its own dynamics that shape how planets and smaller bodies evolve. ʻOumuamua carried information about its home system in its composition, structure, and isotope ratios. Detailed study could have told us about the conditions in its parent nebula, the type of star it formed around, perhaps even the age of its home system. This would have been our first direct sample of another stellar system's material, a cosmic gift that we could only partially unwrap before it disappeared back into the darkness. We also missed the chance to test our theories about how objects survive interstellar journeys. The surface of ʻOumuamua has been exposed to cosmic rays for potentially millions of years, creating a processed layer that could tell us about the interstellar environment. The object's internal structure might preserve information about its original state before the long journey modified its exterior. By studying how ʻOumuamua differs from solar system objects, we could have learned about the effects of interstellar travel on matter, information crucial for understanding both natural processes and the challenges of interstellar spaceflight. The biological implications of what we might have missed are particularly tantalizing. If panspermia is possible, if life can spread between star systems via natural objects, then ʻOumuamua might have been carrying evidence of this process. Even if it wasn't carrying living organisms, it might have had organic molecules, perhaps even complex ones that could serve as building blocks for life. The reddish colour suggests organic compounds might be present on its surface, but we'll never know their exact nature or origin. We might have missed the chance to detect the first evidence of organic chemistry from another star system. As our technology improves, we're developing the capability to detect smaller and fainter interstellar objects. The Vera Rubin Observatory, with its enormous field of view and sensitive detectors, is expected to discover many more interstellar visitors in the coming years. Some of these might be detected early enough in their approach that we can study them in detail or even send spacecraft to intercept them. But for each one we detect, there will likely be hundreds or thousands that pass through unnoticed, too small or faint for even our best telescopes to spot. The story of what we might have missed with ʻOumuamua is also a story about the pace of technological development. If ʻOumuamua had arrived just a decade later, we would have had better telescopes, faster computers, and perhaps spacecraft specifically designed to intercept interstellar objects. If it had arrived a century later, we might have had a network of sensors throughout the solar system, able to detect and track any object passing through. The narrow window between when we developed the capability to detect ʻOumuamua and when it actually arrived highlights how much of astronomical discovery depends on fortunate timing. There's also the haunting possibility that ʻOumuamua's trajectory through our solar system was not random. If it were an artificial probe, its path might have been calculated to observe Earth and the other planets from specific angles or distances. It passed inside Mercury's orbit, giving it a close view of the inner solar system where life exists. Its trajectory took it relatively close to Earth. Not so close as to seem threatening, but close enough to be detected by a civilization with our level of technology. Did we miss subtle course corrections that would have revealed intelligent control? Did we fail to notice patterns in its rotation or acceleration that encoded information? The psychological impact of these missed opportunities extends beyond just scientific regret. ʻOumuamua appeared as disappeared so quickly that it feels almost dreamlike, a cosmic apparition that we can hardly believe was real. The limited data we collected makes it impossible to definitively answer the most intriguing questions about its nature. This ambiguity fuels continued speculation and debate, keeping ʻOumuamua alive in our collective imagination in a way that a thoroughly studied object might not be. In a sense, what we missed has become as important as what we observed. the gaps in our knowledge creating space for wonder and possibility. As we arrive at the final chapter of our contemplation tonight, ʻOumuamua continues its eternal journey through the darkness, somewhere beyond the orbit of Neptune now, heading back into the vast spaces between stars. It carries with it all its secrets, all the answers to questions we desperately wanted to ask, but never got the chance to fully explore. The mystery of ʻOumuamua hasn't been solved. If anything, it has deepened with time as scientists continue to analyze the limited data we collected, and theorists propose ever more creative explanations for its bizarre properties. This continuing mystery, this unresolved cosmic puzzle, has become part of ʻOumuamua's legacy, transforming how we think about our solar system, our galaxy, and our search for life and intelligence beyond Earth. In the years since ʻOumuamua's departure, scientific papers about this enigmatic object have continued to appear in journals, each offering new perspectives, new analyses, new possibilities. The debate over its nature has not cooled, but has instead evolved, becoming more sophisticated as researchers build on each other's work. Some scientists have strengthened the case for natural explanations, proposing ever more exotic compositions and formation mechanisms. Others have refined the argument for artificial origin, calculating what would be required for various technological scenarios. The mystery has become a productive engine for scientific thought, spurring innovations in theory and plans for future observations. The discovery of a second interstellar object, 2I/Borisov, in 2019 has added another layer to the mystery. Unlike ʻOumuamua, Borisov looked exactly like what astronomers expected an interstellar visitor to look like. A fairly typical comet, showing clear outgassing, a visible tail, and spectroscopic signatures of common cometary molecules. Its behaviour was entirely conventional, following a simple hyperbolic trajectory with no mysterious acceleration beyond what its visible outgassing could explain. In many ways, Borisov's normalcy makes ʻOumuamua's strangeness even more pronounced. If interstellar objects can be as ordinary as Borisov, what makes ʻOumuamua so extraordinary? The contrast between these two confirmed interstellar visitors has led to new questions about the population of objects travelling between stars. Perhaps there are multiple classes of interstellar objects, some formed through conventional processes that produce comet-like bodies, others created through exotic mechanisms that result in ʻOumuamua-like oddities, or perhaps ʻOumuamua represents one extreme end of a continuum, with most interstellar objects being more like Borisov but a small fraction having unusual properties. Each new interstellar discovery will help us build a census of what's travelling through the galaxy, but with only 2 confirmed examples so far, we're still in the earlier stages of understanding this population. The continuing mystery of ʻOumuamua has inspired a new generation of mission concepts designed to be ready for the next unusual interstellar visitor. The European Space Agency's Comet Interceptor, scheduled for launch in 2029, will wait at a stable Lagrange point, ready to redirect toward an interesting target, whether a pristine comet from our own Oort cloud or another interstellar object. More ambitious concepts have been proposed, including spacecraft that could chase down interstellar objects using solar sails or ion drives, potentially catching up to them even after they've passed Earth. Some researchers have even suggested keeping a rocket on standby, ready to launch within weeks of detecting an approaching interstellar object, carrying instruments specifically designed to answer the questions ʻOumuamua left unresolved. The mystery has also influenced ground-based astronomy. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, is being optimized partly with interstellar object detection in mind. Its unprecedented combination of aperture size, field of view, and survey cadence means it should detect many more interstellar visitors, potentially finding them earlier in their approaches when detailed study is still possible. Radio telescopes are developing protocols for rapid response to interstellar objects, ready to search for artificial signals while the objects are still within range. The entire astronomical community has become sensitized to the possibility that the next ʻOumuamua could appear at any time. Beyond the scientific implications, the continuing mystery of ʻOumuamua has had a profound cultural impact. It has entered popular consciousness as a symbol of cosmic mystery, appearing in science fiction, stories, documentaries, and countless online discussions. The possibility, however remote that it might have been artificial, has captured imaginations worldwide. ʻOumuamua has become a Rorschach test for our hopes and fears about extraterrestrial contact. Some see it as potential proof we're not alone, others as a reminder of the vast distances and difficulties that separate us from any cosmic neighbours. The mystery has also revealed interesting divisions within the scientific community about how to handle observations that don't fit existing paradigms. Some scientists argue that we should default to natural explanations unless absolutely forced to consider artificial ones, following the principle of Occam's razor. Others contend that when natural explanations require increasingly exotic and unobserved phenomena, artificial explanations deserve equal consideration. This debate goes beyond just ʻOumuamua to fundamental questions about how science should approach anomalous observations and extraordinary possibilities. The ongoing analysis of ʻOumuamua's trajectory has revealed subtle details that add to the mystery. Its approach, velocity relative to the local standard of rest, was remarkably low, placing it in a special frame of reference that seems almost too coincidental. If ʻOumuamua were a random piece of ejected planetary material, we would expect it to have a more random velocity, but its motion suggests it was almost at rest relative to the average motion of nearby stars before our solar system ran into it. This could be chance, or it could be a clue to something deeper about ʻOumuamua's nature or origin. Scientists have also continued to refine models of ʻOumuamua's light curve. The pattern of brightness changes as it tumbled. Some analyses suggest the tumbling might be more complex than simple rotation, possibly indicating that ʻOumuamua is not a rigid body, but has some flexibility or internal movement. Others have proposed that the light curve could be explained by a more complex shape than a simple ellipsoid, perhaps a flattened disk with irregular features, or even a fractal structure with a complicated surface geometry. Each model makes different predictions about what ʻOumuamua actually looks like, but without resolved images, we can't determine which, if any, is correct. The question of ʻOumuamua's composition remains one of the central mysteries. The lack of observable outgassing despite the clear acceleration is unprecedented in our observations of solar system objects. Every proposed explanation for this discrepancy requires assuming something unusual. Either ʻOumuamua is made of exotic materials we've never observed, or it has a structure unlike any known asteroid or comet, or the acceleration is caused by something other than outgassing. The mystery isn't just what ʻOumuamua is made of, but how nature or technology could create an object with such seemingly contradictory properties. The continuing mystery has also spurred theoretical work on the formation and evolution of planetary systems. If objects like ʻOumuamua are common, It implies that stellar systems regularly eject material into interstellar space. This could happen through gravitational interactions with giant planets, stellar flybys, or the death throes of evolved stars. Each mechanism would produce a different population of interstellar objects with different characteristics. By studying the properties of interstellar visitors, we can work backward to understand the processes that created and ejected them, learning about planetary system evolution throughout the galaxy. The biological implications of the Oumuamua mystery continue to fascinate astrobiologists. If life can spread between stellar systems via natural objects, then Oumuamua-like visitors could be the vectors. Even if Oumuamua itself carried no biological material, it proves that solid objects can survive interstellar journeys and arrive at other stellar systems intact. This validates at least the physical possibility of lithopanspermia, the transfer of life via rocks, ejected from one planetary system and captured by another. The mystery of Oumuamua's nature is thus connected to the mystery of life's distribution in the universe. Looking forward, the mystery of Oumuamua will likely persist for years or decades. Unless we develop technology capable of catching up to it, which would require velocities far beyond our current capabilities, we'll never get additional data about this specific object. But each new interstellar visitor we discover will provide context for understanding Oumuamua. If we find more objects with similar properties, it might point toward a natural explanation we haven't yet imagined. If Oumuamua remains unique among a large sample of interstellar objects, its artificial origin might become harder to dismiss. The mystery has also inspired new thinking about active SETI, the deliberate attempt to communicate with extraterrestrial intelligence. If other civilizations are sending physical probes rather than radio signals, how should we respond? Some have suggested we should prepare our own interstellar messengers, designed to be clearly artificial and carrying information about human civilization. Others propose we should focus on detecting and intercepting incoming objects, being ready to recognize and respond to potential messages. The Oumuamua mystery has expanded our conception of what first contact might look like. There's something beautifully humbling about this continuing mystery. Despite all our technology, all our knowledge, all our theoretical frameworks, Oumuamua has left us with more questions than answers. It reminds us that the universe is still full of surprises, that our understanding is still limited, that there's so much we don't know. This humility is valuable in science, preventing us from becoming too confident in our models, keeping us open to unexpected discoveries. Oumuamua has been a cosmic reminder to stay curious, to keep looking, to be ready for the unexpected. The philosophical implications of the mystery run deep. If Oumuamua is natural, it shows us that nature can create things that look artificial to our eyes, challenging our ability to distinguish between natural and technological phenomena. If it's artificial, it means we've been visited by technology from another civilization, even if just their defunct hardware, fundamentally changing our cosmic status. Either possibility expands our understanding of what's possible in the universe. The mystery itself, regardless of its eventual resolution, has already changed us. As you drift towards sleep tonight, perhaps you can find peace in this unresolved mystery. Not every question needs an immediate answer. Some mysteries are more valuable for the questions they raise than for any answer they might provide. Oumuamua has given us a gift, not the gift of knowledge, but the gift of wonder. It has reminded us that the universe is still capable of surprising us, that there are still discoveries to be made that will challenge our fundamental assumptions about reality. Consider that right now, at this very moment, ʻOumuamua continues its journey through interstellar space. It has passed beyond the reach of our telescopes, beyond the gravitational influence of our sun, back into the realm between stars where it spent millions of years before briefly visiting us. It tumbles onward in the darkness, carrying its mysteries with it, a cosmic enigma that touched our awareness for just a moment before disappearing back into the vast unknown. The mystery of ʻOumuamua connects us to the deepest questions humans have asked since we first looked up at the stars. Are we alone? How did we get here? What else is out there in the darkness? These questions don't have easy answers, and perhaps they never will. But the ask in itself is important. It's what makes us human. This curiosity about our place in the cosmos, this desire to understand, this willingness to contemplate mysteries that might never be solved. In years to come, when new interstellar objects are discovered and studied, we'll look back on ʻOumuamua as the first, the pioneer that opened our eyes to the reality of interstellar visitors. Whether its mysteries are eventually solved or remain forever enigmatic, ʻOumuamua has earned its place in history. It has changed how we see our solar system, not as an isolated island, but as a port of call for cosmic wanderers. It has changed how we search the skies, now watching for visitors from beyond, and it has changed how we think about the possibility of contact with other intelligence. Perhaps not through radio signals or flying saucers, but through subtle, ambiguous messengers that require us to question our assumptions about what's natural and what's not. The continuing mystery of ʻOumuamua is a reminder that we live in a universe full of wonders we're only beginning to discover. Each answer we find reveals new questions. Each mystery we solve opens doors to deeper mysteries. This is the beauty of scientific exploration. It's not a journey toward final answers, but an endless voyage of discovery, where each new understanding shows us how much more there is to understand. As sleep begins to take hold, let your mind drift with ʻOumuamua through the cosmic darkness. Imagine it tumbling slowly through the void, this mysterious messenger that briefly visited our corner of the universe. Whether it's a natural wonder or an artificial artifact, it has served its purpose. It has made us wonder. It has made us question. It has made us look more carefully at the cosmos and our place within it. And in doing so, it has given us a gift more valuable than any answer, the gift of cosmic curiosity that will drive us to keep exploring, keep questioning, keep wondering about the mysteries that surround us in this vast and beautiful universe. The story of ʻOumuamua is far from over. Somewhere out there in the darkness between stars, it continues its eternal journey, carrying secrets we may never unlock. But its brief passage through our solar system has left an indelible mark on human consciousness. We now know that we are visited by objects from other stars. We know that the galaxy is more dynamic and interconnected than we imagined, and we know that even with all our technology and knowledge, the universe can still surprise us with mysteries that challenge our understanding of what's possible. Perhaps that's ʻOumuamua's true message, not encoded in its trajectory or its composition or its acceleration, but in the simple fact of its existence and our detection of it. The message is that we're ready to see such things, ready to ask such questions, ready to contemplate possibilities that previous generations couldn't imagine. We're a species on the threshold of cosmic awareness, just beginning to understand our place in a galaxy full of wonders, and ʻOumuamua, whether natural or artificial, was our first confirmed glimpse of the larger cosmos beyond our sun's familiar realm. Tonight, as you finally surrender to sleep, you carry with you the knowledge that we live in a universe where objects travel between stars, where the impossible journey has already been made, where mysteries drift through the darkness waiting to be discovered. ʻOumuamua has come and gone, but it has left us changed, more aware of the cosmic drama playing out around us, more prepared for the next visitor that emerges from the interstellar darkness. And perhaps, in our dreams tonight, we too can drift among the stars, following ʻOumuamua's path through the cosmos, exploring the mysteries that await us in the vast spaces between the stars, knowing that we are part of something infinitely larger and more wonderful than we ever imagined.